Hello, everyone. You're about to hear and watch a little question and answer session that Sir Tony and I have prepared. The questions were prepared in advance, so there are no surprises for us, but who knows what's going to happen as we go on. So I'll begin by asking Tony a few questions. So tell me, first questions are about your education, how it interested and motivated you and prepared you to be a computer scientist. Do you have any relevant memories from your early school days?
Oh yes, they stretch right back to my primary school. I was a studious and precocious child, and not always popular among my fellows. They gave me the nickname Prof, which was not always kindly intended, but it didn't prevent me from later taking professorship as my career goal.
Well, was there someone who started you in the direction of computer sciences, being a computer scientist?
Yes, I think so. That was in my secondary school. During free afternoons, I used to read books in the school and public libraries, also books by Bertrand Russell, the English logician, philosopher, and political activist against nuclear weapons. As an adolescent schoolboy, I was attracted first by Russell's book on marriage and morals. It recommended free love as a forerunner and as a concomitant of marriage. It's notorious that Russell himself had extensive experience of both. My highest qualification in mathematics was a B in advanced mathematics, a school certificate taken at the age of 14. However, I have always liked mathematics and read books about it in my spare time, even at school. They included Mathematics for the Million by Lancelot Hogben. But my subsequent education for the higher school certificate was in the classics, Latin and Greek.
What did you do as an undergraduate at Oxford that turned out to be most relevant to your career?
Well, it was really another extracurricular activity. Immediately on joining my college, I joined a group of second-year mathematicians on my staircase. We gathered regularly late in the evening in one of my neighbours' rooms to study logic. Our text was Van Quine's Methods of Logic. I think my fellow students shared with me my curiosity to find out why mathematical reasoning and proof of mathematical theorems seemed so much more credible than all other forms of human reasoning, scientific, legal, historical, statistical, etc. During the following years, I studied Russell's Introduction to Mathematical Philosophy. It presents a popular, even amusing in places, account of the foundations of the arithmetic and of various number systems, natural numbers, integers, fractions, and reals. I still have a copy of his book, together with Quine's book, in my bookshelves for repeated consultation.
Your CV says that your highest academic degree was a Bachelor of Arts, and you studied classical literature, languages, history, and philosophy. Now, in those early days, people came to computer science from lots of directions, but philosophy?
Yes, indeed. It was considered unusual, but it was claimed by the professors that holders of this particular degree were suited to any subsequent career. And I think maybe I've stretched the limits of that a little bit. In the degree course, my favorite subject was philosophy, and it gave me my strong impetus towards computer science. In those days, computers were just beginning to attract attention among philosophers, including my tutor, John Lucas, who who wrote 3 subsequent books on computational philosophy. Also philosophers of the mind, interested in computer program execution as an analogy for human thinking. Even the general public was reading books like Giant Brains or Machines That Think.
Well, why didn't you go on for a doctorate?
Well, I applied for a research studentship in philosophy, but didn't get a grant.
Well, what did you do instead?
Oh, many things. On graduation, I became liable to 2 years national service, which I spent learning Russian in the Royal Navy. One of the 2 years I spent at London University School of Slavonic Studies. At the end of my service, I obtained a qualification as a Russian interpreter. I've exercised my Russian on many subsequent visits to Eastern Europe.
Well, you then returned to Oxford, and this time to study for a 1-year certificate in statistics. Why statistics?
Well, that was the profession that I intended to pursue myself, in preference to the more usual manager training jobs traditional for arts graduates at Oxford. And I got a grant for it. I was also attracted to the subject of probability and by the philosophical question of what kind of knowledge was expressed by a statement of probabilities of future events. No single observation could ever refute such a statement, provided it wasn't a statement of probability 0 or 1. I gave my own answer to this question in a paper that I read to the Graduate Philosophical Society at Oxford. The typescript for it is stored in the Oxford University Scientific Archive. In statistics, I was particularly interested in principal component or factor analysis, which was then used to evaluate the intelligence of British school children. To understand it, I read an undergraduate text on matrices and eigenvalues, which provided coefficients for linear regression, supposedly predicting academic capability. Again, I was exploring the analogy between human and artificial intelligence. Modern machine learning theory still uses matrices to seek predictive formulae, but without the restriction of linearity. It seems to work. I also took advantage of a course by a visiting logician, Hao Wang. He had just implemented on the IBM 704 a program which proved all the theorems in the first 9 chapters of Russell and Whitehead's Principia Mathematica. I also enjoyed a week's introduction to computer programming. As a final exercise, I wrote a program which computed the value of a 2-person game. I had found the saddle point algorithm from von Neumann and Morgenstern's theory of games, which I also happened to be reading at the time. And finally, for pocket money, I translated a Russian collection of articles entitled Theory of Mathematical Machines, edited by Yuya Basilevsky.
You spent your last student year as an exchange student in Moscow. How come?
Well, firstly, it was just for an adventure in the first instance, but also to practice my skills in Russian. I chose to study in Andrei Kolmogorov's Department of Probability. He had provided the mathematical foundation of probability theory as an application of measure theory. During my sojourn in Moscow, I learned bits of measure theory from the excellent book by Paul Halmosh in the university library. I attended lectures from Kolmogorov and his colleagues. Not surprisingly, I lacked the mathematical background to understand Russian graduate level mathematics in the subject. Now, while in Moscow, I received an invitation to apply for a job as a senior scientific officer to work on a project for machine translation of scientific Russian into English. They were using a computer, the ACE, which followed the architecture of Turing's Pilot ACE. It was made with valves, mercury acoustic delay lines, and magnetic drums. Not a very pleasant machine to program if you weren't Turing. I read an article then on syntax by Chomsky in the Lenin Library and wrote in Russian my first published journal on the subject. But I soon realized that machine translation was impossible, especially using magnetic tapes, and later declined the offer. I took up an interest in the topic again 50 years later when the increased power of computers made it possible. Using machine learning, of course.
Well, thank you. Perhaps I'll ask later whether you found out from that person doing the Whitehead and Russell proofs whether it was really true that volume 3 contained 50 blank pages, as the rumor has it. But now it's your turn to ask me some questions.
Okay, well, I'll start with the same question. What is your educational background?
Well, in brief, I studied mostly math. Then I became interested in physics, but I realized I wasn't smart enough to be a physicist. So instead, I just got a PhD in math just to get me out of school.
Good. I think that is something that occurred to many people, including my friend Edgar Dijkstra. But he got his PhD writing an accurate description of a computer that had just come out in the Netherlands. And invented things like semaphores.
Well, it's true. In my time, there were language requirements for a PhD, and I believe one could use as one of those language a computer language. But I didn't have to do that.
That was, I think, perhaps wise. How did you get into computer science?
Well, I had summer and part-time jobs programming, and that led me eventually to a job that involved helping to design what would today be called an operating system, and then doing some things that would actually be called research.
Right, I'm answering the same question myself. I can time it a bit more accurate. It was in 1960 when I invented Quicksort, and in the same year I took a job with a computer manufacturer which made small scientific computers, and I learned the whole of the foundations of computer science in the best possible way on the job. So what started you working on concurrency?
Well, I read an article in the Communications, the ACM, about somebody invented a mutual exclusion algorithm, and I just thought it was too complicated. So I submitted a paper with a very simple two-process solution, and a couple of weeks later, I received a letter back from the editor pointing out the mistake in my algorithm. Well, that had two results. First, I was determined to solve that damn problem, and the result of that was the bakery algorithm. The second was that it taught me that concurrent algorithms needed reliable proofs.
And what enabled you to find the bakery algorithm, an algorithm that people still study almost 50 years later?
Well, I think what it was is that other people at the time looked at mutual exclusion either as a math problem or even worse, as a language problem. What constructs could you use to make it easy to implement mutual exclusion? But I regarded it as a physics problem. You had to build two physical devices that wouldn't do something at the same physical time. And I think it was looking at it in that different way that led me to a different kind of algorithm.
Yes, I tend to think of a bakery because my clinic in the hospital uses that technique to order a queue for attention by the nurses and specialists.
You should tell them they should provide cakes when they do that.
Indeed. How did thinking of physics affect your work on concurrency?
Well, probably the most obvious example was my time clocks paper, which was a simple application of the ideas of special relativity to distributed systems. But also, I liked solving problems. And years earlier, I would have little sequential programming problems. But in sequential algorithms, at that time, the problem generally meant doing something faster. But in concurrency, it meant doing something that no one had been able to do before. And I found that more fun. But I was only interested in problems that solved what I found to be a real physical problem. And I think that's why some of my solutions turned out to be useful later.
I can well believe that. I too have a similar experience of finding special relativity is a very good way of describing abstractly the effect of concurrency inside computers. Now you've worked a lot on formal methods. Was that due to your maths background?
Well, my interest in formal methods grew out of my desire to prove the correctness of the algorithms that I wrote. And it started out figuring out how to write reliable proofs. But then the question started to arise, well, what was I trying to prove? What did correctness mean? And I think the major benefit of my math education was that I wasn't impressed by mathematics. And many people seem to feel that finding pretty math to describe something was in itself a worthwhile achievement. Matter of fact, there was one paper that I reviewed that my comments were that the only real problem this author solved was understanding his own notation. But for me, math was just a tool whose main benefit was allowing me to express things rigorously. The math wasn't important. It's what it expressed that was important. And I believe that the math should be as simple as possible.
Oh, I hardly agree with that sentiment. How simple were you able to make the maths?
Well, it took me about 15 or so years, but what I finally came up with is a temporal logic called TLA. And aside from ordinary math, it had just three operators: prime, box, and another operator that's really there just for philosophical reasons.
Oh.
Now, prime had actually been used for a long time outside temporal logic. When a variable x refers to the value of x in the current state, and x prime refers to its value in the next state. That notation had been used before. But so it meant that you write a formula x prime equals x plus 1 describes an operation that adds 1 to x. As for box, intuitively, box of a formula f means that the formula f is true from this time on. So effectively, I only had to add the two operators prime and box to ordinary math.
TLA is a logic. What people use is the TLA plus language that is based on TLA. What's that language like?
Well, engineers usually think of TLA plus as a programming language. They think of everything as a programming language, but it's a programming language with two constructs, the prime operator and a syntax for making definitions. And it also has expressions. Now, in most programming languages, and in fact, in at least some specification language, expressions are built out of really simple primitive data types, numbers, booleans, strings, and arrays. And in TLA plus, an expression can be absolutely any mathematical formula. The system is described by two formulas. There's an initial predicate, which is an ordinary math formula, and a next state predicate. It's also an ordinary math formula, except it contains primes because it's talking about the current state and the next state. Now, the next state predicate is usually a disjunction of a bunch of formulas, which are defined separately and given a name, that describe the possible atomic operations of the system. The structuring is provided by definitions, which is, the definition is the most amazingly powerful and simple way of structuring things ever invented by mankind. For example, an atomic step may change the value of a variable x to equal the Riemann integral from 0 to 1 of some function f. That's the definite integral of elementary calculus. Now that action is written just x prime equals integral of three arguments, 0, 1, and f. And the integral operator itself can be defined in about a dozen lines of TLA plus. And the TLA spec actually is the conjunction of the initial predicate conjoined with boxed the next state predicate. That actually specifies safety, which means what the system is allowed to do. Liveness, which says what it must do, requires an additional formula in which box appears. And that formula is just a few lines long, if engineers bother writing it at all.
Am I right in saying that an atomic step may include many simultaneous actions at a given level of granularity, at least? Like a structured simultaneous assignment that's used in optimizing compilers to abstract from the sequence of consecutive assignments in the program.
Indeed.
Dijkstra,
for example,
Dijkstra called it multiple assignment.
no. Oh, indeed. For example, it could say that every computer in a network at the same instant computes the set of all prime numbers. Not an action that I've ever had occasion to write, but no problem writing it.
So you could deal with fences, for example, in relaxed memory.
Oh, trivial.
I think that is an absolutely crucial attribute of a specification language, and indeed, because either at an abstract or at a concrete level, you want these things to appear to be atomic actions at the level of granularity for the person who is actually using the definition. The fact that it is implemented by many actions of a computer must be completely hidden from you.
Oh yeah, in TLA plus, it's trivial to express any kind of synchronization mechanism that you want to add. There's nothing built into the language for that. There's no need for it.
That's wonderful. How do you write math in TLA plus?
Well, TLA plus uses ordinary notation for things like arithmetic, logic, and sets. I invented some notation for things mathematicians don't have rigorous notation for. For example, specifying a function, a simple thing you'd think they'd have a good notation for. And also for a notation for some idioms that occur often in specifying systems that mathematicians don't typically use. But the actual math is what I believe I learned in high school, but which any programmer or mathematician or computer scientist ought to learn in their first year at the university. And a language that can define the Riemann integral in a dozen lines isn't going to have any trouble representing the kind of math that you learned in high school.
That's, I think, certainly true. Does it really work in practice?
Yes. People describe real algorithms and high level of abstractions of real industrial systems in TLA+. You know, people who make real money at building programs like Microsoft and Amazon and places like that. The complexity of the system is expressed with the ordinary math, not in terms of complicated operators like those used in programming language or esoteric temporal logic operators. Mathematicians have spent centuries making math simple and rigorous, and I think they've done a pretty good job of it.
I can't help but agree. With great pleasure indeed. Building a system is usually taken to mean writing code. How do you deal with code?
Well, we teach students algorithms, not just how to write code. And that's because even if you're the best C++ coder in the world, that's not going to help you design an algorithm. High-level abstractions are another name for algorithms. System builders need high-level abstractions of their systems before they code them. That's what TLA Plus is for. Now, there are plenty of tools available to help them write the code. So TLA Plus isn't for that. It's for getting them to think at a higher level.
Yes, I certainly agree with you there. Thank you for this fascinating account of the elements of TLA and TLA Plus. Now, let's move on from our own work and treat some more general questions, which we think will be of interest to those of you attending the Heidelberg Laureates Forum. I'd like to ask Leslie, what areas of research are you currently engaged in?
Well, I don't do much research now. And in fact, I've never sat down and said to myself, I'm going to do some research, or I'm going to develop a theory of concurrency. Actually, I did sit down and do that once a long, long time ago, and I quickly realized that I wasn't going to get anywhere with that. But throughout my career, I would just stumble on a problem, very often from reading a paper. And if it seemed interesting and fun, I'd try to solve it. The most recent problem I stumbled on came from a talk I heard Fred Schneider of Cornell give about hyperproperties. Now, an ordinary property is a property of a single execution. And a hyperproperty is a property involving multiple executions. Hyperproperties were inspired by security problems. For example, one security hyperproperty requires that any two system executions that start with the same publicly visible state produce the same publicly visible behavior, regardless of what's going on in the secret part of the system. I realized that since a system's behaviors are described in TLA as an ordinary formula, a hyperproperty could be expressed as a TLA formula containing multiple copies of the system, each using a different set of variables, and each copy representing a separate behavior. So Fred and I worked out the details, and we just finished a paper showing how the TLA Plus tools could be used to verify that a system satisfies a hyperproperty.
Well done.
The last research I did before hyperproperties came from a paper I received from Martina Badi about 4 or 5 years ago. Now, about 30 years ago, Martine and I published a paper called The Existence of Refinement Mappings that became fairly well known. And to prove that a system implements a spec, it's sometimes necessary to add auxiliary variables, variables that don't change the behavior of the actual variables that describe the systems, but are used for the proof. And one kind of auxiliary variable that have been used for years is a history variable, a variable that remembers what happened in the past. Now, our paper introduced prophecy variables that predict what will happen in the future. And they were really elegant. Mathematically, they just looked like history variables with time running backwards. Very cute. There was just one tiny little problem with them. I found them absolutely impossible to use for verifying real algorithms. Now, the paper that Martine sent me recently, 4 or 5 years ago, introduced a way to make them a little easier to use. But there was still, I thought there must be a better way. And I started thinking about how to verify his examples. And I quickly found a simple, very natural way to handle his examples. And it generalized to a new way to define prophecy variables that was simpler and more general than our original way. And I could use them to verify real published algorithms. And why hadn't I thought of this property variable when we wrote our original paper? Well, it's because at the time I didn't have TLA. Thinking in terms of TLA made it easy to find this kind of prophecy variable. So these are two pieces of research in which TLA has helped me find solutions. And that's happened in other cases as well.
Yes, I think the first realization that what you've discovered is significant is to recognize, is to come up with the question, why didn't I think of this before? And that is really most satisfying.
Okay, now my turn to ask you that question. What research are you currently engaged in?
Well, it was Russell who first, Russell's exposition of the foundations of arithmetic that inspired and informed my lifelong interest in the foundations of computer science. My speciality has, of course, been theories of programming. Each theory, in my view, should guide the development process for programs, including the specification and proof of programs, both large and small, and even programs written in a great variety of programming languages, ranging over declarative, functional, deductive languages, as well as procedural languages, many of which contain concurrency, probability, real time, and so on. Fortunately, each language shares many features and properties with the others. Important distinctions between the features can be incredibly simply described, as you do in the algebra of arithmetic, by simple variation of some of the algebraic axioms. A lot of the mathematics starts with associativity, commutation, and idempotence of operators. And differences between languages are captured by the addition of new axioms or by simple adjustment to other simple algebraic axioms. And for the past 30 years of my research career, I've worked towards the goal of unifying these theories in the same way that Russell showed how to unify a variety of kinds of arithmetic. On this foundation, I hoped it would be possible to develop large programs with components expressed in a variety of languages, using a library of programming methods reusable like current class libraries, which are declared and called in programs, and to develop and exploit development tools which implement each feature of those languages separately so they can be reused in other languages which have the same feature. This flexibility of algebra to deal with differences which really dominate the models of the algebra is extremely valuable. I believe that they will define the true structure of computer science in the same way as other sciences describe their branches as variations or consequences of the simple and powerful laws of nature. Now, I shall ask about the next question, which is, unless you'd like to make a comment, no matter. What advice would you give to a young researcher in computer science?
Well, hi there, young researchers out in cyberspace. This is for you. And I'm afraid I can't give you useful career advice. The world and computer science have changed too much since I started out, and your career path is going to be a lot different from mine. I can just give you some general advice and platitudes. First of all, write, and write, and write some more. Why should you do so much writing? Well, you may think your profession is doing research, but your profession is really writing. You write papers. You just create different plots than novelists and biographers do. And you should learn to write well. And the way to learn to write well is by writing. Make everything you write a masterpiece, whether it's a thesis, a piece of code, or an email. And also, welcome criticism of what you've written, even when the critic seems stupid and he just doesn't understand. If the critic doesn't understand, that's your problem. You should have made him understand. And don't just write for others. You should also write just for yourself. And the reason for doing that is stated in one of my favorite quotes. It says that writing is nature's way of showing you how fuzzy your thinking is. You don't understand something unless you can explain it clearly in writing. And for computer scientists, I like to add that math is nature's way of showing you how fuzzy your writing is. If you can't express something in math, then you probably don't really understand it. Math helps you express ideas and to think rigorously about them. Unfortunately, few mathematicians know how to do math rigorously. They don't even know how to write proofs. Just think about that, you mathematicians out there. But that's another story.
Yes, indeed. Quite a long one, I expect. I absolutely endorse everything you say about writing. That is the method of my research. And I try to follow what you have advised our audience to do in all my research activities.
I'm glad to hear that. And now, what's your advice to our young researchers?
Oh, that's nice. Enjoy. Have fun. These are the two imperatives for successful research. If you do not enjoy it, you'll never endure the long periods of concentration required to make significant advances. In your theoretical research, in experimentation, in improving the technology of engineering practice, or delivery of results to its beneficiaries, you must, above all, believe in it and be enthusiastic about it. You should think of your current research problem in every spare moment, in the morning and in the afternoon, but not in the evening or at night. Reserve your night for the sweet dreams that I wish you. You'll be surprised how often a new approach or a solution will be presented to you when you wake up the next morning. Often, perhaps most often, the idea will turn out, by the end of the next day, of course, to be a dead end. Or it may turn out to be a non-problem, which is also one of the best solutions. But occasionally it will lead to a simple solution that makes it all worthwhile. My next advice is to make an early and explicit choice in your career of the general area of your research, a choice that will last you all your professional life. This is entire contrast with Leslie's problem-driven approach to his career, of which I also applaud, but I didn't follow it myself. Well, it's part of what you should do, and the other part should be somehow related to the long-term goals of your research career. I made such a choice when I moved from my first job in the computer industry to being the head of a department of computer science at the Queen's University of Belfast. This was in 1968. I came across a paper of Bob Floyd on assigning meaning to programs. Well-known paper in computer science. This triggered my formalization of Hoare logic, which used a structured programming language in place of Bob's flowcharts. It was this structure which facilitates the piecemeal design and verification of programs of arbitrary size. It led to my choice of program verification as my lifetime area of research. I conjectured that even on my retirement, 32 years ahead, the results of my research would still not be ready to be adopted by industry. And I would be glad of this, because when industry recognizes that they need a solution, they flood the field with resources on a scale that no academic could ever match. Then I would have to give way to the industrial competition and find work and work up a new research area and gain background and experience in it, which might not be so easy in middle age. Fortunately, my original conjecture was correct. On retirement, 32 years later, I accepted an offer of a job as a senior scientist at Microsoft Research Limited in Cambridge. Before visiting the Microsoft main establishment in Redmond, I circulated project managers of the development division, not the research division, asking if any had experience of assertions. I visited those who replied positively in their offices in Redmond. They were all using assertions as checkpoints in their code to help them to identify and trace the errors of testing programs. Then the scales fell from my eyes. I realized that both verification and testing were using the same technology, assertions, in a common goal of improving the speed of delivery and quality and reliability of software products. So in the last 20 years of my research, 15 of them spent in the employment of Microsoft, I have renounced all the principles which I preached as an academic about the preferability of proving programs over testing them, and concentrate instead on reconciling these two previously opposing positions. And I have applied this tenet to all my rival computer theorists who proposed solutions different from mine. Robin Milner's CCS is different from my CSP. Leslie Lamport's TLA is also different from it. So they were all my rivals competing for industrial attention, which was a very bad thing, because if a manager receives a proselyte who attempts to persuade him, if two different theoreticians can't agree on a theory, then the theory is not ripe for exploitation. A very sensible conclusion that the managers used to draw. So I decided in this respect that I would build links to all my rival theories and abandon my previous sermons about the preferability of my own work. And this I summarized by saying I would grow old disgracefully. My final recommendation is to the mathematicians and physicists in the audience to just plant the idea, why not study computer science, seeking problems that might be soluble by your own particular research specifications and research interests and specialization. Perhaps by some simple and abstract formalization. Some of you might even stay on to work with computer scientists to integrate your mathematical concepts and results into a mathematical proof assistance that are currently in use for program verification. It is they, rather than the programmers, who should munch up the complexity that is involved in actually delivering computer solutions. So I conclude my talk with my recommended salutations. Enjoy, have fun.
Well, thank you, Tony. And I hope that we have managed to confuse the young researchers with our very different career histories, because at their age, they should be confused and not have any certainties that are guiding them in life yet. But one thing we both agree on is that you should have fun. So we hope you're having fun at the HLF, and will continue to have fun at the HLF and as you go forward. And one reason you're having fun at the HLF, because there are these wonderful people who have worked very hard to make it possible. I can't thank all of them, but I would like to thank Ruth for, especially, and also thank Tom Geller and his crew for making this recording.
Thank you very much.
Bye.